The starting balance of an investment account is €100. The account earns interest at an annual rate of 5.25%. Assuming there are no further withdrawals or deposits other than interest that gets deposited, find the total amount in the account after 10 years if the interest added to the account is if the interest is added to the account A, annually, B, quarterly, or C, continuously. So every single moment this interest is being added. Right, so for part A it should be really quite simple, but I will write out the formula which is in the formula book, which says FV equals PV 1 plus R over 100k to the power kn. So in the case of part A, we're looking for future value. We have present value, which is €1,000. So FV equals €1,000 times, well, it's 1 plus R is the rate as a percentage, so it's 5.25 over 100. Remember, K is the number of compounding periods per year. So if the interest is added annually, there's only one compounding period in a year. So K is just 1, so I'm going to leave it. And again, this Kn just becomes N, and N being the number of years. So that's just 10. So that comes out, if I do it on a calculator, that comes out at 1,668.096016. So we haven't been asked for a specific amount of accuracy, so you should always default to 2 decimal places for money. So we will call that, I think that's euros, 1668.10. Okay, so for part B, we can still use the same formula. We can say FV equals, so it's going to be PV 1000 times 1 plus the rate as a percentage, 5.25 over, then the 100k becomes 100 times the number of compounding periods per year. So if it's compounded quarterly, or interest is added quarterly, there's 4 compounding periods in a year. So this must be 4. And the power must be 4 times 10. So 4 times 10. So you can simplify that a bit if you want to, or you can go straight to put it in the calculator, which probably I would do a bit of both, I guess. That comes out at, in euros, 1684.695,003. So again, 2 decimal places for money. We will call that 1684.70. Okay, so that's just using a standard compound interest approach. This is sort of when we're compounding in discrete periods. So in between those quarters, there's no addition of money. Nothing's happening there. And for when it's compounding annually, there's only one time each year when this interest is added. When we have this continuous growth model, which we're going to look at now, that's when it's just all the time this interest is being accrued. So every single moment. It's quite hard to think about, really. Certainly in the context of interest, I find it quite hard to think about. But if you think of, say, a plant growing, well, it's growing a little bit all the time. So it probably makes a bit more sense then. Unfortunately, this formula is not in your formula. There's nothing about compound growth in your formula book, but it is on the syllabus and you need to know a bit. So this we're going to call is the amount at any given time. In this case, the time unit is years. It doesn't have to be years, but it is in this case. Equals P, in RP is going to be present value, E is the number E, to the power RT. Now this R is actually different, so I'll just label a few. This is going to be F, the AT is just future value, P is present value, E is just E, it's a 2.72-ish, but it's a rational number that never ends. R in this case is not 5.25, it's a rate as a decimal. So it will be 0.0525. e.g. 5.25 as a percentage is converted to a decimal, you just divide it by 100. So it's not naturally embedded in the formula as it is here. And t is just exactly the same, it's the number of years. So we're going to have a after 10 years, the amount after 10 years is going to be p present value 1000 times e to the power of 0.0525 times 10. So you might, depending on the calculator you've got, it might be safe to use a bracket there, but if you're not sure, use it, because it won't make you wrong using it, but not using it could make it wrong if it's an old calculator in particular. So if you're wondering where the e function is, I'll make sure it's included in a picture somewhere, but it's usually, if you can see a little button with an ln, natural log, and it's usually just above that, so e to the x like that. It's usually just above, so you have to press shift to get to it, but it does depend on the calculator you're using. So this comes out at, in euros, 1690.458848. So again, 2 decimal places for money, 1690.46. So you can see, when you're compounding continuously, although it's not a huge difference, you certainly do get more. So it's only sort of €6 more, not even that actually. But the more compounding periods you have in a given time frame, if you're compounding, if it's interest, as in you're increasing, then it will become more and more and more. But the effect will become less and less as n gets bigger and bigger.